Welcome back to my channel. Subscribe my channel for more videos.
Welcome. Today we're diving into combinational logic, a fundamental concept in digital design. I'm Sindhu Devi, and we'll explore how these circuits work without memory, producing outputs based solely on current inputs. This is Unit 2, and it's key to understanding how complex systems come together. Let's get started. Let's talk about the decimal adder, also known as the BCD adder. This circuit adds numbers in binary-coded decimal format, where each decimal digit from 0 to 9 is represented by a 4-bit binary number. Because of this, normal binary adders can't just add these numbers directly. They need extra correction logic to keep the results valid within the decimal range. So, the BCD adder is designed specifically to handle this, making sure each digit stays between 0 and 9 after addition. Let's talk about the BCD adder, a clever circuit made up of 4 full adders linked together. Each full adder looks at 2 BCD digits plus a carry from the previous stage. It outputs a sum bit and a carry bit that feeds into the next adder. Now, when the sum of 2 BCD digits goes over 9, it's no longer a valid BCD number. To fix this, the circuit adds 6, that's 110 in binary, to correct the sum. This way, the BCD adder always gives a valid BCD result. Let's start by figuring out how many digits our BCD adder needs to handle. Remember, each BCD digit uses 4 bits. For the adder's structure, we'll connect full adders in series, one for each digit. When we add a new digit, we also need to include the carry from the previous stage. Our full adder circuit will add 2 4-bit BCD digits plus a carry-in, producing a sum and a carryout. These are the key steps to design a BCD adder. Let's start by linking the full adders together in a chain. The carryout from one stage becomes the carry-in for the next, moving up the order. Next, we add a correction step. This kicks in when the sum of 2 BCD digits goes above 9. At that point, we add 6 to adjust the result and carry over to the next stage. Finally, we test the whole setup with various BCD inputs to make sure the addition and correction work perfectly. When we apply the correction rule, we add 6 to our calculation. But why 6? It's not random. This number adjusts our result to fit the system we're working with, making sure everything aligns properly. Think of it as a small fix that keeps the whole process accurate and reliable. Adding 6 helps us correct any offset and brings our numbers back on track. It's a simple step, but an essential one. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's start with our first example. This will help us see the ideas in action, grounding the theory with something concrete. As we move through, keep an eye on how the key concepts come alive here. It's one thing to understand them, but another to spot them working in the real world. This example sets the stage for everything that follows. Here's another example to help us see the concept in action. This one builds on what we've already covered, showing how the ideas come together in a real-world scenario. By examining this example closely, we can better understand the practical steps and the impact they have. Let's take a moment to explore the details and what they reveal about the bigger picture. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. When the sum of 2 numbers is 9 or less, their BCD sum and binary sum match perfectly. But once we go beyond that, the two sums differ by 6, that's 110 in binary. This difference is key to understanding how BCD addition works. Now, let's dive into the table and explore the logic behind adding this 110 value. This will help us see exactly when and why this adjustment happens. Now we're adding the binary sequence 110, which equals 6, but only to the second half of our table. The conditions for this are specific. First, if C' equals 1, that covers cases 16 through 19. Next, if both S3' and S2' equal 1, that satisfies cases 12 to 15. Finally, if S3' and S1' equal 1, that handles cases 10 and 11. So our logic boils down to this expression: C prime plus S3 prime times S2 prime plus S3 prime times S1 prime equals 1. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about why a BCD adder is so useful in digital logic. First, it ensures decimal precision. It adds decimal numbers directly using binary-coded decimal digits from 0 to 9. This means no errors sneak in from converting between base 10 and base 2. Second, it simplifies decimal arithmetic. That makes BCD adders perfect for systems where decimals rule, like cash registers, calculators, or real-time clocks. In short, they make decimal calculations straightforward and reliable. Let's talk about why BCD adders are so useful in digital systems. First, they work seamlessly with common display technologies like 7-segment displays, which show numbers in decimal form. This means the output can be displayed directly, no extra conversion needed. Next, BCD adders help spot errors. They can detect invalid digits quickly, making error correction simpler and more reliable. Finally, they enable efficient circuit designs tailored for decimal math, speeding up processing and keeping circuits less complex. It's a smart solution all around. Let's talk about some of the drawbacks of BCD adders. First, they use more memory compared to binary digits, which means they take up extra space in systems that rely on them. Second, they're limited to decimal digits only 0 through 9, so they can't handle values outside that range without additional conversion steps. Finally, because they need special correction for decimal numbers, their arithmetic operations tend to be slower than binary adders, which can slow down the whole system's performance. When working with BCD arithmetic, compatibility can become a real challenge. Some techniques and algorithms are optimized for binary arithmetic, so mixing the two can cause issues within the same system. On top of that, BCD adders are more complex than their binary counterparts. They need extra correction logic to ensure the results stay valid, which means larger circuits and more complicated designs overall. These factors can make implementing BCD arithmetic a tricky balancing act. A binary multiplier is a digital circuit designed to multiply two binary numbers. It works much like the paper and pencil method we learned in school, by calculating partial products for each digit, then adding them up while shifting left each time. Because binary digits are just zeros and ones, multiplication becomes straightforward. Multiplying by 0 always gives 0, and multiplying by 1 leaves the number unchanged. That's why AND gates create the partial products, and adders combine them into the final result. Let's talk about the binary multiplier, a fundamental circuit in digital electronics. It multiplies two binary numbers, which is essential for computers. Sometimes it's called an add-shift adder because of how it works. Most digital multipliers create partial products first, then add them together using binary adders. Now, an adder, or summer, is a circuit that performs addition. Adders are key components in arithmetic logic units, the brains behind many processors. Together, these parts make multiplication possible in digital systems. Let's take a look at different types of bit multipliers and how they handle numbers of varying sizes. A 2 by 2 bit multiplier works with numbers that are just 2 bits long, both the multiplier and multiplicand. Moving up, a 3 by 3 bit multiplier deals with 3-bit numbers, producing a product that's 6 bits long. Then there's the 4 by 4 bit multiplier, which multiplies 4-bit numbers and outputs an 8-bit product. The key idea is that the product's bit size equals the sum of the two input bit sizes. Now, let's look at binary multipliers of different sizes. We start with the 2-bit multiplier, which can be built using either a 2-bit full adder or individual single-bit adders. Then, we move to the 3-bit multiplier, which can also use either 3-bit full adders or single-bit adders. Finally, the 4-bit multiplier uses a 4-bit full adder to handle the multiplication. This progression shows how complexity scales with the number of bits and the choice of adder design. Let's break down how a binary multiplier works. First, it creates partial products by multiplying each bit of one number with each bit of the other. Basically, an AND operation. Then, it adds all these partial products column by column to get the final binary result. The design of this logic circuit changes with the bit size, getting more complex as the numbers grow. Its main job is to multiply binary numbers quickly, speeding up calculations in digital systems like computers. It's a lot like how we multiply decimal numbers, just in binary form. When we multiply binary numbers, the process is actually quite similar to decimal multiplication. We have a multiplier and a multiplicand, and their combination gives us the product. But here, we're only dealing with zeros and ones, which simplifies things a lot. The first rule is straightforward. 0 times 0 equals 0. This means whenever we multiply 0 by 0, the result is always 0. It's a simple but essential foundation for binary multiplication. Let's look at some basic rules of binary multiplication. When we multiply 0 by 1, the result is 0. The same goes for 1 multiplied by 0. It also equals 0. But when we multiply 1 by 1, the product is 1. This last case is straightforward. There's no need to carry or borrow anything. These simple rules form the foundation for more complex binary calculations. Let's take a look at a truth table for binary multiplication. It shows how two inputs, the multiplicand and the multiplier, combine to produce an output, the product. When both inputs are 0, the product is 0. If either input is 0, the product stays 0. Only when both inputs are 1 do we get a product of 1. This simple table captures the fundamental logic behind binary multiplication. Let's talk about the 3 by 3 binary multiplier. This is a type of combinational logic circuit designed to multiply two binary numbers, each up to 3 bits long. When you multiply these, the result can be as large as 6 bits. That's because the output needs to hold the full product. This circuit handles all that multiplication instantly, without needing any memory or sequential steps. It's a fundamental building block in digital systems, where quick, small-scale multiplication is needed. Let's break down how a 3-bit binary multiplier works. We start with two numbers, the multiplicand and the multiplier, each made up of 3 bits. When we multiply them, we get 3 partial products. These partial products come from multiplying each bit of the multiplier by the entire multiplicand. To add these partial products together, we use a combination of a 3-bit full adder and some single-bit adders. This setup forms the logical circuit that handles the multiplication, as shown in the figure. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Here, we're looking at a detailed breakdown of multiplying two 3-digit numbers, each digit labeled from 0 to 2. The multiplicand digits are A2, A1, and A0, while the multiplier digits are B2, B1, and B0. Each row shows partial products, multiplying each digit of the multiplicand by a single digit of the multiplier. Notice how these partial products align, with zeros added as placeholders to keep everything in place. Finally, these are summed up, including any carries, to get the final result. This step-by-step approach is the foundation of long multiplication. Let's break down how the carry bits are generated in this addition process. When we add A to B0 and A1 B1, the carry bit is raised. Then, by adding the sum of those results with A0 B1, A0 B2, and A1 B0, another carry bit can be produced. This chain continues, generating 2 carry bits that carry over as we add A to B1 and A1 B2, creating 2 more carry bits in the same way. This approach is straightforward compared to other methods. The circuit uses 3-bit full adders to combine 3 partial product terms. Notably, the least significant bit of the first partial product isn't added further. It directly becomes the LSB of the final output. In essence, one 3-bit full adder handles the first 2 partial products, and a second one adds the third partial product to that sum. It's a neat, efficient design. Let's break down how we figure out the number of gates needed for this multiplier circuit. The AND gates come from multiplying the number of bits in the multiplier by those in the multiplicand. That's m times n for the adders, we use m-1 to get the full output width of m plus n bits. So, for a 3-bit multiplier, that means 9 AND gates and 2 3-bit full adders. When we add the partial products, the least significant bit of each sum goes straight to the output, while the rest feed into the next addition stage. Let's talk about the magnitude comparator, a fundamental building block in digital logic. It takes two binary numbers, A and B, and compares them directly. The circuit then tells us if A is greater than B, equal to B, or less than B. This simple comparison is crucial in countless applications, helping systems make decisions based on numerical relationships, all in real time and without any memory. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. This circuit compares two numbers bit by bit, starting with the most significant bit, the one that holds the greatest value. At each step, it checks the bits in both numbers. If the bit in the first number is bigger, the circuit sets the output to show that the first number is greater. If the bit in the second number is bigger, it sets the output to show the first number is smaller. This way, it quickly figures out which number is larger without checking every bit. When comparing two numbers bit by bit, the circuit starts at the first pair and checks if they're equal. If they are, it moves on to the next pair and keeps going like this until every bit has been checked. But if it finds a difference at any point, it stops immediately and outputs whether the first number is greater or less. Only if all bits match does it confirm the numbers are equal with an A equals B signal. When it comes to building a magnitude comparator, there's more than one way to do it. We can use a mix of XOR, and OR gates, or take a different route with a series of full adders linked together. The best choice really depends on what matters most, whether that's speed, how complex the design is, or how much power it uses. Each approach has its trade-offs, and that's what guides our decision. Let's talk about the single-bit comparator, a simple but powerful tool. It compares two individual bits, each with its own input. The comparator then gives us three outputs: less than, equal to, or greater than. This way, we can directly see the relationship between two single-bit numbers. The slide also shows the truth table, which lays out exactly how these outputs correspond to every possible input combination. It's the foundation for comparing larger binary numbers. Now that we've seen the truth table, we can write logical expressions for each output condition. For example, a greater than B is expressed as A and not B similarly. A less than B is not A and B when A equals B. It's either both not A and not B, or both A and B together. From these expressions, we can move forward and derive a single, combined formula that captures all these cases. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Now, by applying these Boolean expressions, we're able to build a logic circuit that performs the comparison we need. This circuit is the practical result of the theory we've covered so far, turning abstract expressions into a working design. It's the bridge between concept and implementation, showing how logic gates come together to solve real problems. Let's talk about a 2-bit magnitude comparator. This device compares two binary numbers, each made up of 2 bits. It has 4 inputs, 2 bits from each number, and 3 outputs. These outputs tell us whether one number is less than, equal to, or greater than the other. Essentially, it's a simple circuit that helps us understand the relationship between two small binary values. The truth table that follows shows all the possible input combinations and their corresponding outputs. Here, we see a table comparing pairs of inputs labeled A and B, each with 2 bits. The table shows all possible combinations and the results of 3 comparisons. Whether A is less than B, equal to B, or greater than B for each input pair, only one of these conditions is true. This helps us understand how binary values relate to each other, which is fundamental for decision-making in digital circuits and computing logic. Here, we see a grid of zeros and ones, a simple binary pattern laid out in rows and columns. This kind of table often represents data in its most basic form, where each number can stand for a true or false condition, on or off state. It's a way to visualize complex information in a structured, easy-to-compare format. As we move forward, keep in mind how these patterns can be the foundation for more intricate systems and analyses. Here, we see a table filled with a pattern of ones and zeros. While it might look like a simple grid, this kind of data often represents something deeper, like a set of conditions, features, or binary states. Each row could be a unique combination, showing how different variables interact or switch on and off. Understanding these patterns helps us decode complex systems, revealing the underlying logic or behavior we want to explore. It's a snapshot of structured information, waiting to be interpreted. Now, from the truth table we just saw, we can move on to drawing the Carnot map for each output. This step helps us visualize the logic more clearly, making it easier to simplify. Here, we focus on the output labeled a greater than b. The K-map organizes the truth values so patterns emerge, patterns that guide us toward a simpler, more efficient expression. This is where the real power of Boolean simplification starts to show. Here, we see the truth table for the output labeled a equals b. This table lays out every possible combination of inputs and shows us when the output will be true or false. It's a simple but powerful way to verify how the logic behaves, making sure the output only signals true when A and B actually match. Truth tables like this one help us understand and design reliable digital circuits. Let's take a look at the truth table for the output A less than B. This table breaks down every possible combination of inputs A and B, showing when the output will be true or false. It's a clear way to see the logic behind the comparison. Exactly when A is smaller than B. Understanding this helps us build circuits or programs that make decisions based on numerical order. Now, we're looking at how the logical expressions for each output come directly from the Carnot maps we analyzed earlier. These Boolean expressions break down the conditions for when A is greater than B, when A equals B, and when A is less than B. By translating these expressions into logic gates, we can build a circuit that compares the two inputs accurately. This step is crucial. It bridges the theory of simplification with the practical design of the comparator circuit we need. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about a 4-bit magnitude comparator. This device compares two binary numbers, each made up of 4 bits. It takes 8 inputs, 4 bits from each number, and gives us 3 outputs that tell us if one number is less than, equal to, or greater than the other. The key to understanding when one number is greater lies in checking the bits from left to right. If the highest bit of A is 1 and B's is 0, A is greater. If those bits are equal, we move to the next bit, and so on, until we find a difference that decides the comparison. Now, let's explore when one number, A, is less than another. B. There are 4 specific cases where this can happen. First, if the highest bit of A is 0 and B's is 1. Or if those bits are equal, but the next bit in A is 0 and in B is 1. This pattern continues down through the bits. Finally, A equals B only when every single bit matches exactly. It's a step-by-step comparison, bit by bit. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Now, let's break down the bit comparator for an n-bit input. The total number of combinations is 2 raised to the power of 2n. Out of these, the equal combinations, where A equals B, are 2 to the power of n. The unequal combinations are the total minus the equal ones. And since the greater than and less than cases are symmetrical, each accounts for half of the unequal combinations. This gives us a clear formula to understand how these comparisons distribute. Comparators play a crucial role in CPUs and microcontrollers. They're used in control systems where physical variables, like temperature or position, are converted into binary numbers and then compared against a reference value. This comparison helps the system make decisions. You'll also find comparators in process controllers and servo motor control, ensuring precise operation. Beyond that, they're key in security applications, like password verification and biometric systems. In short, comparators are everywhere, quietly keeping systems accurate and secure. Comparators are straightforward tools designed to quickly compare binary values. They're essential for fast decision-making in digital circuits, helping systems respond instantly. Because of their simple design, comparators can be easily integrated into complex components like processors and arithmetic units. Their modular nature means we can scale them up, comparing multi-bit numbers efficiently. This flexibility and speed make comparators a key advantage in digital design. Comparators have a limit on how many bits they can compare at once. When we need to handle larger bit sizes, the circuit becomes more complex. This added complexity doesn't come for free. It leads to higher power consumption. So, while comparators are useful, their design challenges and energy demands grow as we push for bigger, more detailed comparisons. A binary decoder is a digital circuit that takes binary-coded inputs and converts them into a unique output. It does the opposite of an encoder. When you feed it a binary value, like 10, it activates just one output line that matches that value. All the other outputs stay off. This is crucial in systems where binary data needs to control multiple outputs, like memory addressing or display controls. With n inputs, a decoder creates 2 to the power of n outputs, ensuring only one output is active for each input combination. Let's talk about active low inputs. In some binary decoders, the signals are considered active when they're at a low logic level, that's 0. When the signal is high, or 1, it's inactive. This might seem backwards at first, but it's actually quite common. Active low logic helps reduce noise and saves power, especially in integrated circuits. It's a clever way to keep things running smoothly and efficiently. Binary decoders come in several variations, each designed for different needs. The standard binary decoder takes n binary inputs and converts them into 2 to the power of n unique outputs. For example, a 3 to 8 or 4 to 16 decoder. Then there's the priority decoder, which assigns importance to inputs. If multiple inputs are active, it only signals the highest priority one. Finally, the error-detecting decoder checks for invalid codes and triggers an error signal if something's wrong. These types cover a wide range of practical uses. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about the 2 to 4 decoder, a simple but powerful digital circuit. It takes 2 binary inputs and uses them to activate exactly one of 4 outputs. Only one output is on at any time, while the others stay off. Essentially, it translates the 2-bit input into a single active line out of 4 possible options. This decoding process is fundamental in digital systems, helping to direct signals precisely where they need to go. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about a binary decoder. It takes a set of binary inputs and turns on just one output, the one that matches those inputs. All the other outputs stay off or low. For example, with 2 inputs, A and B, a 2 to 4 decoder has 4 outputs. Each output corresponds to a unique combination of A and B, so if both are 0, only the first output is on. Change the inputs, and a different output lights up, but never more than one at a time. This selective activation is what makes decoders so useful. Now let's talk about the enable input, labeled E. This extra input acts like a master switch for the outputs. When E is 0, all outputs are forced off, no exceptions. But when E is 1, the outputs follow the usual logic based on inputs A and B essentially. Each output is combined with E using an AND operation. This way, the decoder only activates when enable is on, giving us precise control over when the outputs respond. Let's talk about how a decoder can help us build any logic function. First, we express the function as a sum of minterms. That means writing it as a combination of input conditions where the output is 1. Next, we pick a decoder that matches the number of inputs, generating all possible minterms. Finally, we connect the decoder outputs for the minterms we need to an OR gate. The OR gate then combines these signals to give us the function's final output. It's a neat way to simplify complex logic. Binary decoders bring a lot to the table in digital logic. First, they offer increased flexibility, letting us select one output from many using just a simple binary code. This makes them useful in all kinds of applications. Next, they boost performance by turning a serial input into multiple parallel outputs, speeding up how information moves through a system. Finally, they improve reliability by cutting down the number of lines needed, which means fewer chances for errors to sneak in. It's a smart way to keep things efficient and accurate. Let's look at some downsides of using binary decoders in digital logic. First, they tend to be more complex circuits. More components are needed compared to simpler options like demultiplexers. Second, their use is pretty narrow. They only work well when you need to convert a serial code into parallel outputs. And finally, they have a limit on how many outputs they can handle, since that number depends directly on the inputs and the binary code itself. Let's explore how binary decoders play a vital role in digital logic. First, they help select specific memory locations by decoding address inputs. That's memory addressing. Next, they generate control signals inside microprocessors by decoding instruction codes. These are the control circuits. They also drive displays, like lighting up LED segments based on binary inputs. Beyond that, decoders create chip select signals for memory or peripherals, decode digital communication data, and even help identify and correct errors. They're everywhere, quietly making digital systems work. Let's talk about encoders, a key part of digital circuits. An encoder takes multiple input signals and converts them into a binary code. Usually, only one input is active at a time, and the encoder outputs a binary number that shows which input is active. The number of inputs is often a power of 2, like 4 or 8, and the outputs are fewer, just enough bits to represent those inputs. This makes it easier to handle and transmit data efficiently in digital systems. For example, a 4-to-2 encoder turns 4 inputs into a simple 2-bit code. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's take a closer look at the 4-to-2 encoder. It has 4 inputs, Y3 through Y0, but only one input can be active, or 1, at any given time. When that happens, the encoder converts which input is active into a 2-bit binary code at the outputs, labeled A1 and A0. This slide shows the logic symbol for that process. Encoders like this are key building blocks in digital systems, helping us simplify multiple input signals into a smaller, manageable output. Here, we have a truth table that maps specific inputs to their corresponding outputs. Each input is a 4-bit code, and the output is a 2-bit result. Notice how only one input bit is set to 1 at a time, and each unique input produces a distinct output. This kind of table helps us clearly understand the relationship between inputs and outputs, which is crucial for designing logical circuits or systems that rely on precise input-output mappings. Here, we're looking at the logical expressions for 2 signals, A1 and A0. A1 is defined as the combination of Y3 or Y2, meaning if either Y3 or Y2 is true, A1 will be true. Similarly, A0 depends on Y3 or Y1. These expressions help us understand how different inputs influence the outputs in a clear, logical way. It's a simple but powerful way to map relationships in the system. Let's take a closer look at the 8-to-3 encoder, also known as the octal to binary encoder. It has 8 input lines, labeled Y7 down to Y0, each representing an octal digit. On the output side, there are 3 lines, A2, A1, and A0, which produce the binary equivalent of the active input. Essentially, this encoder converts an octal input into its binary form, making it easier to process in digital circuits. The diagram here shows the logic symbol for this encoder. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Here, we see a clear example of how inputs map to outputs in the system. Each input is a single active bit, moving from right to left. Notice how the output counts up in binary, from 0 to 7, as the active input bit shifts position. This table shows a straightforward encoding. Each unique input corresponds to a unique output pattern, making it easy to identify which input is active just by looking at the output. It's a simple, elegant way to translate signals. Here, we see the logical expressions for the outputs A2, A1, and A0, each defined as a combination of inputs Y7 through Y1. For A2, the output is true when any of Y7, Y6, Y5, or Y4 are true. A1 depends on Y7, Y6, Y3, or Y2, and A0 is true if Y7, Y5, Y3, or Y1 are true. These expressions help us understand how the outputs relate to specific input signals in the system. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about the decimal to binary encoder. It typically has 10 input lines, one for each decimal digit from 0 to 9. Then, it has 4 output lines, which represent the binary-coded decimal, or BCD. What this encoder does is take the decoded decimal input and convert it into a BCD output. This process lets us work with decimal numbers in a binary system. The figure here shows the logic symbol that represents this encoder. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Here, we have a clear mapping between inputs and outputs. Each input is a single active bit moving from right to left, representing a unique position. The output, in turn, is a 4-bit binary number that counts up as the active input bit shifts. This table shows how a specific input pattern translates into a corresponding output value, a fundamental concept in digital encoding and decoding. It's a simple yet powerful way to convert one form of data into another. Here, we see the logical expressions for 4 outputs, A3, A2, A1, and A0. Each one is defined as the sum of specific Y variables. For example, A3 is the sum of Y9 and Y8. A2 combines Y7, Y6, Y5, and Y4. A1 includes Y7, Y6, Y3, and Y2. Finally, A0 is the sum of Y9, Y7, Y5, Y3, and Y1. These expressions help us understand how each output depends on different inputs in the system. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about a 4-to-2 priority encoder. It has 4 inputs, Y3 down to Y0, and 2 outputs, A1 and A0. The key idea here is priority. Y3 has the highest priority and Y0 the lowest. So if more than one input is active at the same time, the output will reflect the input with the highest priority. It's a way to simplify multiple signals into a smaller, meaningful code, based on which input matters most. Here, we see a table that maps inputs to specific outputs. The inputs are represented as 4 bits, Y3 through Y0, and the outputs as 3 bits, A1, A0, and V. Notice how certain input patterns, like when the first bit is 1, always produce the output 111. Other patterns use excess as wildcards, meaning those bits can be either 0 or 1. This table helps us understand how different input combinations control the output signals in a clear, logical way. Now, let's focus on how we use Karnaugh maps to simplify logical expressions. Here, we're looking at the expression for A1. The K-map helps us visualize and reduce the complexity of this logic function, making it easier to implement in circuits. By grouping ones and eliminating redundancies, we get a cleaner, more efficient expression. This step is crucial for optimizing our design and ensuring it runs smoothly. Here, we see the logical expression for A0 laid out clearly. This formula captures the exact conditions that define A0 in our system. Understanding this expression helps us grasp how different inputs combine to produce the desired output. It's a crucial step in breaking down the problem into manageable parts and sets the stage for optimizing or implementing the logic efficiently. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about a tricky problem with simple encoders. When all inputs are low, the output is 0, but 0 could also mean input 0 is active. That's confusing. Now, if more than one input is high at the same time, the encoder can't tell which one to encode. It might give the wrong output. To fix this, we assign priorities to inputs. That way, the encoder always picks the highest priority active input, avoiding errors and confusion. Let's look at what makes this encoder stand out. It's highly reliable and accurate, delivering precise results every time. The resolution is higher, so we get finer detail. It offers low-cost feedback, making it budget-friendly without sacrificing quality. Integrated electronics keep things compact and efficient. By combining optical and digital technology, it brings the best of both worlds. Plus, it's designed to fit seamlessly into existing applications, making upgrades smooth and straightforward. These benefits really add up. Let's talk about magnetic radio interference and why it matters here. Encoders can be sensitive. Dirt, oil, and dust can easily contaminate their surfaces, causing issues. They're also vulnerable to interference from direct light sources, which can disrupt their signals. These factors highlight some key drawbacks and disadvantages of encoders that we need to keep in mind when designing or maintaining these systems. Understanding these challenges helps us find better solutions. Encoders play a vital role across many fields. They help computers process information, keep motors running at the right speed, and guide CNC machines with precision. You'll find them in industries from manufacturing to medicine, as well as in data routing and signal processing. Their versatility makes them essential in so many technologies we rely on every day.
Thank you for watching my channel. Please do like, share and subscribe my channel.